One drawing change can look like a practical shortcut. In Kansas City, it quietly redrew where thousands of pounds would go. On July 17, 1981, two suspended walkways inside the Hyatt Regency collapsed during a crowded tea dance. The fourth-floor bridge fell onto the second-floor bridge, and both crashed into the lobby. 114 people were killed. Investigators did not find a freak load or exotic material failure. They found a connection carrying a force it had never been verified to survive. One continuous hanger rod had become two. At the critical joint, the load had almost doubled. To see why, ignore the whole hotel and follow one vertical line. The atrium had walkways at the second, third, and fourth floors. The second sat directly below the fourth. In the original drawing, a continuous steel rod ran from the roof, through the fourth-floor box beam, and down through the second-floor box beam. A nut and washer supported each beam from below. That meant each walkway passed its own weight directly into the same continuous rod. The fourth-floor connection carried the fourth-floor walkway. The second-floor connection carried the second-floor walkway. Simple load pass, but the connection itself was already too weak for the building code. The continuous rod was awkward to fabricate. Installing the lower nut meant threading a long section of rod, so the shop details split the hanger into two sets. The upper rods ran from the roof to the fourth floor. The lower rods ran from the second floor and stopped at the fourth floor beam. Now the second floor walkway was hanging from the fourth floor walkway. At the upper connection, the load was no longer just W4. It was W4 plus W2. The National Bureau of Standards calculated the design load rising from about 20.3 kips to 40.7, essentially double, and it doubled an already critical condition. Box beam was made from two steel channels welded toe to toe. Underneath it, a washer and nut pushed upward or the walkway pulled downward. As people filled the atrium, the fourth floor connection had almost no reserve left. Investigators estimated only about 63 people across the two walkways and concluded the collapse occurred far below the code design load. The likely first failure was at the east end of the fourth floor middle beam. The beam split along its weld. The washer and nut pulled through the open steel. One connection released, then the remaining connections failed almost immediately. The two stacked walkways fell together. This was not one bad drawing made in isolation. The structural design left important connection details unfinished. The fabricator proposed the two-rod arrangement. The changed shop drawings passed through contractor, engineer, and architect review. Yet investigators could not find final calculations showing the new loads or a safety factor for the connection. The original detail already violated the code. The change made it worse. Responsibility was spread across companies, documents, and approvals, but the calculation that mattered was never closed. The third-floor walkway, offset and independently suspended, did not collapse. The geometry of the load path, not defective steel, made the difference. The lesson is not never change a drawing. Construction depends on changes. The lesson is that every safety-critical change must restart the verification loop, redraw the load path, recalculate every affected connection, review the assumption independently, then confirm that the built structure matches the verified design. A signature proves that a document moved. It does not prove that the forces were recomputed. The same principle applies to software interfaces, industrial piping, aircraft maintenance, and supply chains. When a component becomes easier to build, ask what new burden moved somewhere else. At the Hyatt Regency, one practical change moved the weight of an entire walkway onto a connection that was already too weak.